In this paper, we present the acquisition, modeling, and rendering of time-varying BRDFs, or TV BRDFs. The properties of virtually all real-world materials change with time, causing their BRDFs to be functions of time. Here we show 6 spheres rendered with some of our acquired time-varying BRDFs, including watercolor, oil paints, spray paints, fabrics, joint compound powder, and household dust. In order to capture these time-varying materials, we have built a simple high-speed robotic rig as shown here. The light source is held by a robot, orbiting in a vertical plane around the sample plate. 4 digital cameras are mounted on an aluminum frame and lie in a perpendicular plane to capture the change of materials. To ensure that specular highlights are captured by the top camera without occlusion by the light source, the sample plate is tilted by 12 degrees from the horizon. This system allows for very fine sampling of light directions in the incident plane. A full BRDF scan takes about 36 seconds and corresponds to a single time instance in our time-varying measurements. With this system, we have acquired the first time-varying BRDF database, composed of 41 samples which are paints, including watercolors, spray paints, and oil paints, wet surfaces, including fabrics, plaster, cement, and clay, dust, including joint compound and household dust, and miscellaneous materials. Here we show the plots of the raw data of 3 different materials that we have captured in our database. The small gap in the measurement is due to the occlusion of the sample by the light source. By design, it doesn't coincide with the peak of curves. Then, appropriate analytic BRDF models, such as the Nayar diffuse model, the Torrance Sparrow specular model, and the modified Blind's dust model, are fit to the measurements to obtain a compact set of time-varying parameters. Here we show spheres rendered with parameters estimated from our data. Each row shows a single material varying across time. Note the often dramatic changes in the glossiness and diffuse appearance of the materials over time. Our time-varying BRDF database, model parameters, and their trends will be made available upon publication. Here we show a teapot rendered with the Prussian green oil paint, along with plots of the time-varying model parameters on the side. As Ks decreases and sigma s increases, we see the dimming and diffusing out of specular highlights. In addition, along with the variations of the diffuse color albedos on the bottom, an overall change in the color saturation and hue can be observed on the teapot. The trends of these time-varying parameters can be modeled by our analytic TV BRDF models. Here we summarize the key properties of our analytic models. For paints, the specular albedos and roughness vary at exponential rates. Diffuse colors of drying paints shift within a dichromatic plane in the color space, spanned by the paint color and the surface color. In the case of wet surfaces, the diffuse color shift can be modeled as a straight line in the color space. Furthermore, their surface albedos brighten according to a sigmoidal function. For dust, the specular highlights fall off exponentially and die out in the very early stage of dust accumulation. Our analytic time-varying BRDF models can be used directly for rendering. For example, here we first show a dragon with a white surface. It can be rendered with our captured blue watercolor. A heat source is suspended in the corner to vary the drying rate spatially. We clearly notice the diffusing and dimming of specular highlights and the characteristic diffuse drying patterns. Our analytic models also enable the transfer of the drying effect. Here we have a bunny model with a white surface. We can synthesize the effect of green watercolor drying on a white surface, and apply the synthesized time-varying material to the bunny. Please note the well-preserved temporal variations of the material. Furthermore, we are also able to change the color of the underlying surfaces. In particular, we now use a bird model with a red surface. We are able to synthesize the effect of blue watercolor drying on a red surface and render the bird model. As time goes by, the specular highlights become diffused out, and the watercolor layer thins and transmits more color of the underlying surface. Our final example is a simple application of our analytic model for dust in a tea set scene. Here, dust is accumulating from a circular dust source overhead onto the surfaces with different materials, leading to effects such as diffusing and fading of specular highlights and the overall changes in color saturation and hue. The teapot and teacup are rendered with our acquired data, while the table is rendered with a synthesized material with a low specular component. Due to gravity and surface inclination, Dust is not evenly distributed, and less dust is attached to steeper surfaces. Further, due to occlusion, intricate dust shadows under the teapot and its knob, under the teacup, and on the saucer are formed. In summary, we have presented a comprehensive study of time-varying BRDFs, including acquisition of a database of time-varying BRDFs, analyzing the underlying parameter trends, and developing analytic time-varying BRDF models for the effects of drying of various paints, wet rough surfaces and dust accumulation, and a number of novel rendering applications.